Okay, hi everyone. So my name is Howie, and this presentation is about better Scala builds with the mill build tool. I'll hold the microphone. So about myself, I've been an open source developer since 2012, lots of open source Scala projects, projects like Ammonite, Mill, OSLib, uPickle, FastParse, and many others. I also work professionally at Databricks and Dropbox working on developer tools. So things like CI systems, integration testing systems, multi-cloud infrastructure, IDs, build systems, and so on. I'm the author of the book Hands-on Scala Programming. So the agenda for today is we'll talk a bit about what is Mill. We'll go into a bit more detail into why you may want to use the Mill build tool versus what you already have. And lastly, we'll spend some time talking about how does Mill work. So the first point is maybe what is Mill? So before I go into this, like who here has used Mill before? So some of you have, most of you probably haven't. So Mill is an open source JVM build tool. The project's not that new. It started in 2017 and originally targeted Scala, but now also targets Java, Kotlin, and other platforms. So it does the same thing as SVT, Maven, or Gradle, more or less, but aims to be better and easier to use than SVT, Maven, or Gradle. In terms of Maven, Gradle, it's a lot faster. In terms of SVT, generally it's a lot easier to use and fewer things to go wrong. The documentation is at millbuild.org, so those of you who have your laptops open or your phones open, you can go there and check out more details there that I can't go through in this talk. So to begin with, a simple mill build looks something like this. So on the left, you have the build.mill file. This is equivalent to build.svt or build.gradle or pom.xml, and it defines the structure of your project. So we have the package import boilerplate. We have an object that extends module. We have Scala version, some dependencies, and a standard kind of triple format, similar to what Gradle uses. And you have a nested object, which is a test module, and it pulls in the dependency on the utest library and configures the appropriate test framework. So far, nothing here should be too surprising, and I can show it to you here live. So if I pull this open, cd -- simple Scala, and I can pull up the relevant. Sorry, let me put this down a second. Okay, so on the left, you see the same build we saw earlier on the slide. On the right, let me make this bigger. I have my terminal. I can run mill compile. The first time it takes this, it's a bit slow because it needs to boot up, but after that it gets fast, just like any other JVM application. Foo.compile. I can do foo.run. In this case, the application requires some command line parameters. Application requires a -- text flag, so I need to pass in -- text. Let's say hello world. And this is kind of a dummy application, just uses Scala tags HTML library to render some HTML to standard out. In this case, we say h1, hello world, close tag h1. If I go back to the build file here, you can do foo.test. You can see this just runs a test. See, it supports all the Scala test frameworks. Foo.assembly. This generates the assembly, but if you want to see where the assembly is, you can use show. So this generates the assembly, which is a kind of a fat jar file that you can run outside of mill. So I can run the assembly with -- text hello world, and it just prints it out. So far, nothing here is that surprising. Guys have seen this all before. These are standard kind of build tool functionality. And the main thing that's interesting so far is that your mill build is a Scala program. And it's not a Scala program the way SVT is a Scala program, which is a kind of really complicated DSL built on top of Scala with lots of additional functionality. It's a Scala program in that you have objects. The objects can nest within each other, as objects do. Objects can have methods, as objects do. And the methods can call each other or be inherited or be overridden by other methods. So although this is Scala just like SVT, hopefully it's a bit more familiar to you, and we'll see some more important ways in how that impacts mill later. So we saw the demo, and that's what is mill. So the next obvious question is why mill? You're already using SBT, maybe some fraction are using Gradle or something else, or Basel. So why would you use the mill build tool? And for people coming from the Scala community, I think the main selling points for mill are these three. So it's harder to use incorrectly. Like there's not that many ways you can go wrong. It's somewhat more understandable than SBT, which is a common complaint. Like you have a build, you're cargo culting things off the internet, there's no way for you to figure out exactly what you're doing or know what you're doing. And lastly, it's much more extensible. So SBT has a huge plugin ecosystem, mill also has a plugin ecosystem, but mill doesn't need plugins as much as SBT does because you can often just extend it yourself to do what you need to do rather than what some random plugin author on GitHub needed to do. We'll go through these in turn. So first, about being foolproof. So one of the things we did with mill is we ran comparative benchmarks against the other popular JVM build tools. We have comparative benchmarks against SBT, against Maven, against Gradle. And for this presentation, I'm going to mostly talk about SBT, since that's what we use in Scala community. So I took the Gatling codebase. Gatling's a popular kind of open source load testing framework. They now have a startup around it, I believe. And it's a kind of a medium-sized Scala application. So 80K lines of code, 800 files, 20 subprojects. Not big, not large, kind of medium size. And I took the existing SBT build and I converted it to mill just manually. It took about maybe an afternoon, not terribly difficult. So it's not a production-ready mill build, but it's enough to get all the source files compiling and all the tests passing. So for purposes of comparison, it's complete enough. So the benchmarks I measured were the parallel clean compile all benchmark. You run SBT clean, you compile everything, including the test suite. Clean compiling a single module, incrementally compiling a single module, like let's say after you change a single file, or no op compiling something. You just run compile after you've already compiled everything. What's the overhead look like? So SBT, as you know, has kind of two modes of operation. One is if you run SBT raw from the command line, SBT compile, SBT foo::run, or SBT foo/run, or foo/test. And in this case, the SBT spins up a new serve process each time and can be pretty slow. It also needs to initialize a large amount of in-memory state in order for this to work. And you can see that the cold SBT numbers are relatively slower than the hot SBT numbers in the middle. So hot SBT numbers are what you want to do using SBT, or you should do using SBT to make it faster, which is to create an SBT shell by running SBT in bash, running your commands in the shell. Whenever you update your SBT build definition, you need to make sure you run reload so you don't end up using out-of-date build definitions. If you run something takes too long, you Control-C, you need to remember to reopen your SBT shell before running your next command. And this is all a bunch of work, but in exchange for the work, you get much faster turnaround times because your JVM has a chance to stay around. Initialization can be cached. The compiler and bytecode can become JIT optimized, and generally it's much more performant, albeit some significantly more manual work. So mill is very comparable to the hot SBT workflows in terms of performance. In fact, in some ways, it's a bit faster. Like the parallel clean compile all mills may be a third faster than compiling everything in SBT, even though it's the same files. So these are all just overhead that mill kind of has less of than SBT does. But perhaps the main advantage here is that with mill, you can't accidentally just fall back to the lazy but slow cold SBT, run things from the shell workflow, because in mill you always run things from the shell, and mill will just automatically do the right thing for you. Mill will automatically reload the build definition when it detects changes. Mill will automatically restart the server and keep it running. If it gets killed, but for some reason, maybe Control-C, you kill the server, mill will automatically restart the server next time. So although mill doesn't really have much of a higher theoretical performance than SBT does if you use optimally, mill is just much easier to use optimally so that you don't need to spend so much time thinking about your build tool. Another advantage of mill is in terms of using plugins. So the Gatling project has the following plugins. This is a subset, there's actually more. And these are all actually things that are pretty straightforward that many projects, or almost all projects, will need to do. Most projects will need to create some kind of assembly jars to deploy the binary to run somewhere. Most projects want to run benchmarks. Jupyter is the most popular Java testing framework in the world, so many projects will want that. You want Scalafix, Kotlin, you want some kind of auto-formatter linter thing, which is what Spotless does. And in order to get this basic functionality, in SBT, in Gatling, in this case, we need to pull in 6 different plugins from 6 different organizations, from random people across the internet, and hope that they did a good job writing these plugins and making them correct and effective. So with Mill, Mill does still have plugins, and in this case, we still need a Scala fix plugin. That's the external plugin that someone wrote for Mill. But by and large, most of the things that you do with Mill are built in. So for example, creating assembly jars, which is what most people use native packager for. Mill has assemblies built in, and I just showed it to you earlier. You just run .assembly, you get an assembly, you can run it. JMH, Jupyter, which is JUnit 5, Kotlin, the various linters like Palantir Java format or Scala format, all these are built into Mill. And again, like Mill doesn't let you do more than what SBT lets you do. It's really the same functionality in both sides. But Mill just lets you do it easier, so you don't need to go scrape the public GitHub repositories to kind of find the right plugin for you to use and hope you don't choose one that's abandoned or choose one that's poorly maintained. Like you just use the one that comes with Mill, and it'll generally do a decent job, and it's good enough for you to get started and kind of go very far with your project. So that's about being foolproof, right? It's not about the power of the build tool, because SBT, as you all know, is extremely powerful. It's not about performance. SBT can be fast. It's not about flexibility. It's kind of just how easy it is to get the maximum out of your build tool. Get the maximum performance, get maximum functionality. Mill just gets you there much faster and easier than SBT does, even though it doesn't let you do that much more. So the next point I'm going to look at is the understandability. So SBT is kind of famously opaque and hard to reason about. You know, people can copy stuff off the internet, people can copy-paste their own build definitions, but if I want to ask anyone here, hey, can you please go write a static file preprocessor in order to preprocess our static files at build time so you can deploy them to S3, people might have trouble doing this effectively using SBT. Like they know Scala, they know JVM, they know Linux or whatever, they know web development, but to combine all this with SBT to write like a non-trivial pipeline, like not just setting flags, but actually doing logic, can be remarkably difficult. And after you do it, someone else coming in to figure out what your SBT build is doing can also be pretty difficult. And Mill really helps this by providing really good ID support and introspection tooling. So even if you're not familiar with Mill, your ID can help you poke around the build and really understand what's going on. And we'll see this now. So first is the Chrome profile. So I'm going to go back to my demo. And let me pick the Gatling. I think this should be the Gatling Mill code base. So this is a Gatling build for Mill. It looks about the same as Gatling build for SBT, but slightly different spelling of the various syntaxes. So that's not interesting yet. Let me put this down. So if I run Mill clean in my Gatling Mill code base, again, first time it takes a minute to start up your JVM after that's fast. And I run _compile. So you can see it's doing a lot of things. There's a little terminal kind of prompt on the bottom right-hand side of the screen. You can kind of tell, it tells you what it's doing at any point in time, and it tells you how long it's been taking for each move. So for example, now it's running core, compile, seems to be stuck for a while, but now finishes, it makes a bunch more progress. A bunch of downstream tasks are available to run. And same thing happens with other tasks. So we've run the whole thing, compile the whole Gatling code base to about 23 seconds. Again, this is not much faster than SBT. In particular, it's hot mode. Gatling, Mill and SBT are similar in performance. But let's say I want to ask a question. Why did Mill or Gatling take 23 seconds to compile? Where's the time going? What's running in parallel? What's running sequentially? Where are my long polls that other people are waiting for? What can I do to make this faster if it is too slow for me? So in many build tools, it's pretty difficult to get answers to. You can kind of squint at the prompt that's scrolling by in the terminal and see what's being compiled and try and get some intuition. But Mill provides something much better, which is automatic profile for every build command you run. So if I open up my my output folder, I don't know if you can see this, but there's this Mill Chrome profile file that's automatically generated. It's a JSON file in a particular format. And what it does is it is compatible with how do I get out of this? Okay, here it is. is compatible with the Chrome's // tracing tool. Who here has used a Chrome tracing tool before? Nobody? So for those of you who don't know, Chrome comes with an automatic built-in profile visualizer for multi-threaded programs built into Chrome. It's used by default for people debugging web performance issues, but you can load any JSON file of the right format into Chrome. It's not a very complicated format. It just tells you when did something start, when did something end, what thread was it running on. And it gives you an automatically generated and interactive view of where your time is going. So I'm guessing most of you have Chrome on your laptops already. You may have used this UI before, but you can plug it in right now. It works. And just like that, I can see where is my time going in my Gatling mill build. So you can see at the start, it's doing a bunch of small tasks. Maybe it's checking dependencies and whatnot. And then when it starts compiling things, you can see it compiles here, Gatling JSON path compile, commons compile, quick lens compile. After these three finish, core compile kicks off here. You can see it's taking a while, which is what we also kind of subjectively saw at the terminal. And only after common compile finishes on the right, do a bunch of downstream tasks kick off. And another long pole, so to speak, is Gatling core test compile, which only after that finishes can the other kind of test modules begin compilation. So this is interesting, and it's not just interesting from an academic perspective. Like, this gives us a lot of actionable insight into what we can do. For example, we know that the CPU utilization at the front is pretty good. I'm using all my 10 cores on my MacBook Pro. But in the middle, the CPU utilization, and towards the end, it gets pretty poor, as we are not, although we have 10 cores, we're spending most of the time waiting for these single large modules to compile. And that gives us some actionable like opportunities, right? Like, can Gatling core be broken up into smaller modules that can compile in parallel? That might help. Can you see a bunch of test modules like HTTP tests, JMS tests, some other test modules, all waiting for Gatling core test compile? Do those modules really need to wait for the entire Gatling core test suite to compile to finish? Or do we really only depend on some utilities library or test helpers or test fixtures that it could extract into a separate module and depend on, which would allow all of these downstream test modules to start compiling much earlier? And although the wall clock time may not be different, it will properly saturate out, improve the utilization of our CPU around this time and help the wall clock time finish earlier. So this all happens automatically for free for you using Mill. Every single command you run, you just generate a JSON file. You all have Chrome. You're curious how long it took, load it up, and you can see immediately how many milliseconds every single command took, which ones were in parallel, which ones were sequential, and from there decide what you want to do to help speed up your build. So that's the Chrome profile, one of Mill's very nice built-in utilities. The other one is the visualize command, which offers another view on the structure of your code base. So coming back here. So imagine you're a new programmer who just joined the code base, right? You open up your Gatling code base, you see a whole bunch of files, a whole bunch of modules, 800 files and 80K lines of code, and you're wondering, how does this build work? What relates to what, who depends on what, what's the structure of the build? I see the top level folder layout, but how do these things actually depend on each other and contribute to making the production ready application or code or module or library? So with Mill, you have the built-in visualize flag. I'm just going to search for it in my history. And Mill visualize, which we have down here, basically lets you ask, given a set of tasks, in this case, double underscore means wildcard, so double underscore compile means anything.compile, so all the compile tasks. Given a set of tasks, show me the graph representation of them. How do they depend on each other? So any build tool like Mill or SVT has lots and lots of tasks. You have IV dependencies, you have a source code, you have all sorts of small things that you probably don't care about. And by putting in double underscore compile, it tells Mill focus on these compilation tasks and kind of simplify away the rest. So you see now it generates 5 files, a dot file, a JSON file, PNG, SVG, TXT, the bunch of graph formats, whatever you prefer. If I open up the SVG, you can see that this is the Mill, this is the Gatling Mill builds compilation dependency graph. So you can see that core compile is indeed a bottleneck. This is exactly what we saw earlier in our profile. You can see that only when core compile finishes can the downstream tasks here begin kicking off. And core test compile, again, maybe is another bottleneck that only when this finishes can the downstream test compilation kick off. And this isn't kind of magic, but this is just surfacing the data we already have in your build system and your project. So your build system already needs to know this stuff. Your build system needs to know who depends on who needs to run first, who can run parallel, who can run sequentially. And Mill makes it very easy for you to just ask the build tool, hey, tell me what's going on here. And here you can see exactly what the structure of my program is. And if I'm contributing to this code base, then this really helps me understand at a high level how this program is, how this code base is designed, not just as like a flat set of folders on disk. So that is, coming back to the slides, that is our visualize command. The next thing I'm going to look at is my IDE support. So Mill and SBT both have IDE support. They are both in Scala. IntelliJ, VS Code all support Scala. But we'll see how it's actually quite different between the two. So let me pull out again my Gatling. Sorry, put down the microphone. And I'll make this a bit bigger. So let me open up my build SBT. So let me pull up the right part of the code base. Okay, so like I said earlier, Mill and SBT are both Scala. They have very different syntax, but it's really the same kind of semantics or same intent being expressed. So if we look at Gatling charts in Mill, I look at Gatling charts in SBT, like it's spelled differently, but it's really the same thing is happening, right? So Gatling charts, there's a dependency on Gatling core, there's a test dependency on Gatling core test. In SBT, it's the syntax depends on core, percentage, compile, test. Syntax is a bit different, but whatever, it means the same thing and we can guess what it means. Both have a dependency on charts dependencies, both charts dependencies have dependencies on T-digest and test steps and so on. So far, you can see that both Mill and SBT have quite similar IDE support. Maybe Mill has a few kind of spurious squigglies here that we are fixing the latest version of IntelliJ. What's more interesting is what happens when you start asking questions. For example, let's say I'm a new developer. I didn't know what library dependencies was. So you all probably know what library dependencies is, but there's also this kind of, imagine there are many other tasks you don't know what they do, right? So let's say you find a task you don't know what it does. You know, IntelliJ can tell you library dependencies is a setting key of a sequence of modules, but it doesn't tell you much else. Like where's the docs? Where's the meaning of this? It's just the type. So we love types, but types are not enough. There's more to code than just types. So if I jump to this, I'm left in a bunch of generated code that again tells me nothing except the type. So this is probably just a bug in SBT. Like sometimes it works, sometimes it doesn't. I know it's worked before, but let's say I know how to get to the actual code for this, right? So who here knows how to find where library dependencies is defined? So what you need to do is you need to go to the sbt/sbt repo, keys.scala. And you have to remember it's keys.scala, it's not any other file. There's one file with most, not all, but most of the magic in it. And you can grep for library dependencies. Sorry, I misspelled this. And you can see that, okay, now that I've grepped for this magic file, I know that library dependencies declares and manage dependencies. Okay, so at least I have some documentation, not a lot, but some. But what's next, right? What else do you ask? Who's using this? What does it use? Like, what's going on here? You gave me a string. You have an identifier. You have a type. But comments and types are not the only things to do with the code base. I want the implementation. And if you start grepping library dependencies, there's nothing. So what do you do next? What do you do next is you go to the search bar and just search the entire SBT code base for library dependencies. And whoops. Yeah, and this is how you figure out what tasks do in SBT. Sorry, let me go back to the. So yeah, you'll start seeing it being used. You'll start seeing it being assigned in various build files and. Sorry, I clicked on the wrong thing. Various build files, various Scala files, various test suites, and other random things. And from this, you're meant to figure out what library dependencies does, or what library, who's using it, and what it uses, and how it does it. So good luck to you if you end up in this state. So again, for library dependencies, this is generally kind of not really a problem. You know what it does. But that kind of just reinforces the fact that there's a small number of things you know what they do just from the documentation from Google or from Stack Overflow. And for the rest of it, you just hit the wall. There's no way you can figure it out. You go and just grab the entire SBT source code and maybe you'll be able to figure it out. So for Mill, it's different. So here it's called IVDEPS. It's a bit different name, but whatever, it's the same thing. Immediately, I can see that if I open up IVDEPS, I get documentation. So any IV dependencies you want to add to this module in the format of IV or : name : version for Scala, or single : name : version for Java. So that's nice. What else can you do? You can ask for the super member. So in Mill, the override keyword is optional. I can put it here explicitly if you want to see it, but we make it optional for conciseness. But what's interesting is that these Mill tasks, they're not these magic variables that get assigned somewhere and used somewhere else. They are standard Scala defs, and they override other Scala defs. And in this case, I can see that, okay, it comes from Java module IVDEPS. And like any other Scala code, I can see where is IVDEPS being used. Okay, it's used in all IVDEPS. It's used in transitive IVDEPS. Transitive IVDEPS also uses mandatory IVDEPS. Where does that come from? That comes from here. You can override it. It uses the upstream transitive IVDEPS, so it's recursive. As you'd expect, transitively collecting the dependencies is recursive. If I go back to where all IVDEPS was earlier, you can see it pulls up mandatory IVDEPS and IVDEPS. If I find the usages of all IVDEPS, this one is not a separate file, so it doesn't pull up. But basically, you can see this code is a lot more useful than the code we saw in SBT. So you pull up your keys.class class file, which is what we saw on the right. You look at what Mill gives you on the left, and hopefully you can understand like this is what you expect from ID support in a large Scala code base. And the right-hand side is not what you expect from ID support in a large Scala code base. So Mill isn't doing any rocket science here, just taking the stuff you already have and applying it to your build tool. So I can jump around. Here I have transitive compile class path. It looks at local compile class path. I can jump to that. Local compile class path uses compile resources. What's that? I can jump to that too. Oh, compile resources is like the Mill source path in the folder compile-resources. So these are some very nice things that you can do in Mill that really helps democratize the build for you. Like you're not stuck when you hit something you don't understand. You can keep digging and digging and digging. And even if you can't find what you want on Stack Overflow or Google, you can probably dig through the code base and figure out what you need to do, and the IDE will help you. So back to the slides. That's the IDE support demo. Let me check time. 15 minutes left. So that's understandability. Last point is extensibility. So most build tools require extensions to be published as plugins. I need to do foo, I need a foo plugin. Bar, I need a bar plugin. The foo plugin is unmaintained, well, I'm kind of stuck. The bar plugin doesn't do what I want, I'm also maybe stuck. So Mill, interestingly, lets you write code or import any library from Event Central without needing plugins. So there are plugins. Like earlier we saw the Mill ScalaFix plugin was used to get the ScalaFix integration. But in the absence of a plugin, you can often just write code to do things yourself, and we'll see how. So consider this minimal Scala module, even more minimal than the one we had earlier. No dependencies, no test suite, just compile Scala, in this case 2.13.8. You can compile it and it'll compile Scala. So a custom task in Mill is just a method, def. So you all know defs. I say def line count equals task. Let's say I depend on all source files. That's something inherited from Scala module. Again, the IDE will help you if you don't remember what it's called, what it does. And I map it to the lines, the count of the lines, and I sum them up. That's my line count. So line count is kind of a fake, not very interesting custom task, but just representative of the weird ad hoc things you all need to do in your builds. And maybe you need to package up some strange deployment container format. Maybe you need to create a bill of materials that's servable from your web server so people can inspect and see what's going on. So there are plugins for some of these things, but often there are all sorts of weird requirements that you need, and plugins may not fit exactly what your business needs for your code base. So with Mill, it's very easy to say, well, here's my line count task. It's a custom task, just one line of code. And I can override my resource task to say, OK, write the line count to a text file and append this folder containing a text file to the super resources. And you all already know what override and super do, so I hope I don't need to explain it. And now, when I call mill foo.run, because I've overridden resources, it's going to use a new version rather than an old version, and I will be able to print out at runtime the line count 17. So line count is maybe a very boring custom task. Let's say you want to do something more interesting, like I want to render a HTML page because I need it statically rendered, because I do it at runtime, it's too slow. I do it at application startup time, it slows down my application startup. I want to do it at build time. So with SBT, you probably won't do it at build time. You'll just live with a slow startup, or you'll live with a slow application. But with Mill, it's actually very easy to do this stuff. So Mill does not ship with a HTML templating library. It's a build tool. But Mill has this magic import syntax that allows you to just pull in any library you want and use it in your build. In this case, we put in Scala tags 0.12.0. I can then import the Scala tags code, and I can then convert my line count into a HTML snippet that just uses Scala tags right there. And let me just show this to you live. So close this. Custom. So over here on the left, I have the line count thing that we saw earlier. You see, I can show line count, it prints 17. I can say mill foo.run, it'll print line count 17. It's able to fetch the code resource at runtime and print it. I won't show the code. It's straightforward Java code or Scala code. So if I try to import scala tags.text.all.here, you'll see it's not happy because Mill doesn't ship with Scala tags. But I can import iv comly howie Scala tags double colon 0.12.0, and then I can just reload my IDE. Mill integration should take a second or two. OK, now it's done. This spurious warning. And now Scala tags is integrated into my build system. I can jump to it. I can look at the jars on my IntelliJ class path, external libraries, and I can start using it. So let's say I want to call this line count HTML. And we could say div h1 line count, not lint count, line count, p, then I just put this in here, dot render. Again, you can see IntelliJ nicely highlights line count down here, needs to be updated as well. It's normal Scala, and IntelliJ, as far as it's concerned, treats it as normal Scala. So I can show line count HTML. It's just a normal task, like any other. Give it a second to recompile my Scala code. OK, here we are. So you can see my div h1 line count p17 on the bottom left. I can inspect line count HTML. It'll tell me, OK, it's on build.mil line 9. That's what I want. Total number of lines in module source files. That's what I wrote up here. And the inputs are all source files, which is what I wrote here. And if I want to see what all source files does, I can just auto-complete it, all source files, and ask Mill. And OK, all individual source files fed into the Zing compiler. You want to know all source files does? Jump to it, and there's a library method called find source files on all sources. And you can keep jumping in to figure out, see what is going, what these things do. So back to the slide. Like I showed this to you working. And again, what's interesting thing here is there is no Scala tags Mill module. There is no Scala tags line count module or plugin. Like we just took in the standard libraries that you already know from Maven Central, Scala libraries, Java libraries. You just pull them into your build and start using them to do the things you need. So even the things you need to do are not the same as the things some guy on GitHub maintaining a plugin needs to do. It doesn't mean you're stuck. It means you can proceed yourself and just get what you need done. So that's what we need. These are 3 reasons for why Mill: the foolproofness, the understandability, and its extensibility. So lastly, let's talk about how Mill works. So at a glance, Mill basically makes you define objects that inherit from classes or traits. And like any other objects and inheriting from classes or traits in Scala, you get methods from these traits. And these methods form a graph, like foo.sources gets used by foo.compile, foo.compile gets used by class path and resources get used by assembly. It forms a graph. And in Mill, this method graph becomes your build graph. So if I override line count, if I add a new method line count here, and I override resources down here, what we saw earlier, the method call graph changes, as we see in the top right. And in the same way, your build task graph also changes. So if I kind of show the sources and assembly down here, just to show you the thing that was actually inherited, you'll see that the graph of the data flow graph through your methods, your sources gets used here, line count gets used here, resources gets used here. It's exactly the same as what we have conceptually in your build. And once we have this graph, we can do interesting things with it. For example, we can parallelize it to show that, hey, the blue things up here do not depend on the red things down here, so blue and red can run in parallel on separate threads. The green foo.assembly on the right needs to wait for both blue and red to finish before it can start. So that's kind of simple and straightforward. Mill gives you, automatically caches all your tasks for you. So line count is automatically cached to outfoo line count.json. Compiles automatically cache to outfoo compile.json with any files in the outfoo compile.destination folder. And yeah, if you want to look at assembly, it's the same pattern. All tasks in Mill are automatically cached with the exact same file system format. And lastly, Mill can handle the invalidation for you. So let's say I add a new file in my resources folder. Well, the resources folder is not my current resource task because that's override, but my super resource task, right? That is one that's being overridden. And Mill has this graph. So Mill can see that, okay, I touched foo super resources. I automatically know I need to re-evaluate foo.resources and therefore re-evaluate foo.assembly. So all these things are kind of nice. But and these are things that almost all build tools do or try to do. But what's most interesting thing here is on the left, the code we use to configure Mill has nothing to do with parallelism, caching, and validation. You don't see any threads, you don't see any futures, you don't see any cache key computation, you don't see any semaphores, mutexes, file system reads or writes, or serialization code. All that's handled for you by Mill. So all you need to do is you just write your so-called straight line business logic in your build. This is actually usually really simple, right? Like I compute a value based on the source files, I override resources and call super. These are all straightforward business logic. And all the caching and validation, parallelism and stuff is all done for you. So that's kind of a quick lightning summary of how Mill works. I won't go into the details here because there's a lot of depth to it. So this is the last slide, and just to wrap up, Mill is an open source JVM build tool. It supports Java, Scala, Kotlin. It's foolproof. It's quite a lot more understandable than tools like SVT, and it's a lot more easily extensible. And the way it works is that Mill modules are just normal Scala objects, and Mill tasks are just normal Scala methods. So all your normal object and method stuff works. Super classes, traits, super override, all those things work just as you'd expect. You already know how they work. I don't need to teach you. And from this module tree and task graph, Mill provides automatic caching, parallelization, validation, and other things that you'd expect from any modern build tool. So the documentation's at millbuild.org. Again, you can go check it out. There's getting started, there's contributing instructions, there's a bunch of bounties there. If anyone wants a few $100s, there's some money on a lot of these tickets. And please try out Mill, let us know how it goes, and I'll now take questions.